Tonight, we're going to go deeper into matter than most people ever realize is possible. Not into atoms, not into protons and neutrons. Deeper, into the place where one of the most familiar forces in the universe, the force that holds atoms together, the force that makes electricity run through every circuit on Earth, the force your phone, your lights, your heartbeat, all depend on, where that force actually comes from. We're going to ask what charge actually is. And the answer physics gives us is stranger than anything you've been told. Because charge isn't stored inside particles like energy in a battery. There's nothing inside the electron that produces it. It's written into the equations of physics themselves. And by the end of tonight, you're going to understand what charge actually is, where it comes from, and why that answer will change how you see every light and every device around you. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something ordinary. A battery. You pull one out of a drawer, slide it into a flashlight, click the switch, and the bulb lights up. Charge moves through a wire and does work. You've seen this 1,000 times. You've probably never stopped to ask what actually moved. The answer your physics teacher gave you is electrons. Electrons carry negative charge from the negative terminal through the circuit to the positive terminal. That's true. That's accurate as far as it goes. But the next question, what is charge? Where does it come from? Why do electrons have it at all? That's where the answer gets uncomfortable. Because physics, at its deepest level, doesn't say charge is a substance. It doesn't say it's a fluid or a property that was sprinkled onto particles during the Big Bang. It says charge is something that emerges. Something that has to exist because of how the universe's mathematics is constructed. And to understand what that means, you have to go back before quantum mechanics. You have to understand what happened when physicists first tried to describe electricity using the language of fields. Because the story of charge doesn't begin with particles. It begins with Michael Faraday in the 1800s, standing in a laboratory in London, watching a compass needle twitch when he moved a wire nearby. Faraday didn't have a university education. He started his career as a bookbinder's apprentice. He read the books he was paid to bind, became fascinated by science, and eventually worked his way into a position assisting the chemist Humphrey Davy. What Faraday lacked in mathematical training, he made up for in the ability to visualize physical phenomena. He thought about electricity and magnetism, not as forces acting at a distance, which was Newton's framework, but as something filling space. When you place a charged object in empty space, Faraday believed there was something real in the region around it. Lines of force, he called them. Invisible structures in the space surrounding the charge that would push or pull other charges moving through that region. This was a radical departure from the prevailing view. The prevailing view was that two charges simply attracted or repelled each other across empty space with no medium in between. Action at a distance. Faraday thought that was wrong. He thought the space itself was doing something. He couldn't fully mathematize the idea. James Clerk Maxwell did that. In the 1860s, Maxwell took Faraday's intuitive lines of force and turned them into a complete mathematical theory. 4 equations. They describe how electric fields are created by charges, how magnetic fields are created by moving charges and changing electric fields, how changing magnetic fields create electric fields, and how the two fields propagate through space as self-sustaining waves. When Maxwell combined his 4 equations, and solved for the behavior of the fields in empty space, he found that disturbances in the electric and magnetic fields could propagate as waves. He calculated the speed of those waves using constants he already knew from electrical measurements. The answer was approximately 300 million meters per second, the speed of light. Maxwell recognized immediately what this meant. Light is an electromagnetic wave, a self-propagating oscillation of the electric and magnetic fields. And charge, in this picture, is the source of those fields. Electric charge is whatever it is that creates an electric field around itself. That was the classical definition. Clean, operational, experimentally useful. But it said nothing about what charge fundamentally is. It defined charge by what it does, not what it is. That deeper question had to wait for quantum mechanics. Quantum mechanics arrived in the early 20th century and broke the classical picture completely. The classical picture said particles were like tiny billiard balls with precisely defined positions and velocities, surrounded by fields they created. Quantum mechanics said that picture was an approximation that breaks down at small scales. At the atomic level, particles don't have precise positions. They have probability distributions. They don't travel along definite paths. They explore all possible paths simultaneously, with each path contributing to the final probability amplitude. The electron in a hydrogen atom isn't orbiting the nucleus the way Earth orbits the Sun. It's in a quantum state that describes a smeared-out cloud of probability. When you measure the electron, it appears at one location. But between measurements, it's not at any specific location. It's in a superposition of all possible locations, weighted by the probability amplitudes that the Schrödinger equation describes. This was deeply unsettling to most physicists who encountered it. It violated every intuition built up over centuries of classical mechanics. But it worked. The predictions of quantum mechanics matched experiment with a precision that classical mechanics could never approach. The energy levels of hydrogen, the specific wavelengths of light that atoms emit and absorb, the way electrons fill atomic orbitals and create the periodic table of elements. All of it followed from the equations of quantum mechanics with mathematical exactness. But there was still a problem. Quantum mechanics, as Erwin Schrödinger wrote it in 1926, was not compatible with special relativity. It treated space and time differently. And special relativity had been established since 1905 as a bedrock principle. The laws of physics must look the same in any inertial reference frame. That requirement is not optional. So a quantum mechanics that gave time a different mathematical status than space was inherently incomplete. Paul Dirac solved this in 1928. He was 26 years old. He wrote down an equation for the electron that satisfied both quantum mechanics and special relativity simultaneously. The Dirac equation. It described the electron as a four-component mathematical object called a spinor. And when Dirac solved his equation, he found something he had not anticipated. The equation had solutions with positive energy, corresponding to the ordinary electron. But it also had solutions with negative energy. What did that mean? Dirac initially proposed that all negative energy states were already occupied by electrons, forming an invisible sea called the Dirac sea. An electron in a positive energy state could not fall into a negative energy state because those states were already occupied by the Pauli exclusion principle. But a hole in the Dirac sea would behave like a particle. A missing negative energy electron would behave like a positive energy particle with positive charge, the opposite sign to the electron's charge. In 1931, Dirac predicted that this antiparticle should exist. He called it the anti-electron. In 1932, Carl Anderson observed it in a cloud chamber while studying cosmic rays. He named it the positron, the first antiparticle ever discovered. And the discovery of the positron vindicated not just Dirac's equation, but the whole conceptual framework it pointed toward. The framework that would eventually be called quantum field theory. Because the modern understanding isn't that there's a Dirac sea of negative energy particles filling the vacuum. The modern understanding is that the electron and the positron are both excitations of the same underlying quantum field, the electron field. Which brings us to the heart of the question. A quantum field is a mathematical object that assigns a value to every point in spacetime. Every point, not just where matter is. Everywhere. The electron field is defined at every location in the universe. In the room you're sitting in right now. In the space between galaxies. At the surface of a neutron star. Everywhere the laws of physics hold, the electron field exists. When the field is in its lowest energy state, what physicists call the vacuum state, there are no electrons. But the vacuum isn't nothing. The field is still there, vibrating with what are called quantum fluctuations, virtual particles popping in and out of existence on timescales too brief to violate the uncertainty principle. The vacuum is not empty. It is a constant churning of potential. When you add enough energy to the electron field in some small region, you can excite it, create a real, persistent excitation. That excitation is what we call an electron. It has definite mass, it has definite spin, and it has definite charge. -1 unit. The electromagnetic field is another quantum field, also defined everywhere, also fluctuating in the vacuum. When you excite the electromagnetic field, you get a photon. Photons are the particles of light. They're also the force carriers of the electromagnetic interaction. When an electron moves, it disturbs the electron field. The electron field is coupled to the electromagnetic field, so the electromagnetic field responds. The disturbance propagates through the electromagnetic field as a wave. When that wave reaches another electron, it pushes the electron field there, and the second electron moves. What you experience as the repulsive force between two negatively charged objects is this exchange of disturbances through the electromagnetic field. But here's what none of this yet tells you. Why does the electron couple to the electromagnetic field at all? Why does exciting the electron field create a disturbance in the electromagnetic field? What is the fundamental reason these two fields are linked? The answer is gauge symmetry. And to understand gauge symmetry, you need to understand phase. In quantum mechanics, particles are described by wave functions. A wave function is a complex number assigned to every point in space at every moment in time. Complex numbers have two components, a magnitude and a phase. The magnitude squared gives you the probability of finding the particle at that location. The phase is an angle. You can think of it like the position of a hand on a clock, anywhere from 0 to 360 degrees, or equivalently, from 0 to 2 pi radians. Here is a crucial fact about quantum mechanics. The overall phase of a wave function has no physical meaning on its own. If you take the wave function of an electron and rotate its phase by some fixed angle, say 30 degrees, but do it everywhere in space simultaneously, the physics doesn't change. The probability distributions are the same. The energy levels are the same. All observable predictions are identical. This isn't an approximation. It's exact. The absolute global phase of a quantum state is not observable. This is called global phase symmetry or global gauge symmetry. The word gauge comes from an older usage in physics, meaning a standard of measurement, but in this context, it refers to the freedom to choose an arbitrary phase reference without changing the physics. Now, here's where things get interesting. What if you want to make this symmetry local? What if, instead of rotating the phase of the entire electron field by the same angle everywhere in space simultaneously, you want to rotate it by a different angle at each location independently? Here, at this point in space, you rotate by 30 degrees. There, 1 meter to the left, you rotate by 47 degrees. Over there, at the other side of the room, by 90 degrees. Each point in space gets its own independent, freely chosen phase rotation. This is local gauge symmetry, and the question is whether the physics can be invariant under this local transformation. If you just take the Schrödinger equation or the Dirac equation and try to apply a local phase rotation, the answer is no. The equations break. They stop being consistent. Here's why. The Dirac equation contains derivatives of the wave function. Derivatives measure how the wave function changes from point to point in space. When you apply a local phase transformation, the phase changes from point to point by a different amount. The derivative of the wave function picks up extra terms because of those varying phases. These extra terms contaminate the equation. They introduce inconsistencies. The physics is no longer the same, unless you add a new field to the theory. A field that compensates for the extra terms generated by the local phase rotation. A field that transforms in exactly the right way when you apply a local gauge transformation, absorbing the extra terms and leaving the total equation invariant. What mathematical object has exactly the right properties to do this? A vector field. A field that assigns a direction and a magnitude to every point in space. Specifically, a field that transforms under local gauge transformations by adding the derivative of the phase rotation function. And the electromagnetic field, described by what's called the four potential in relativistic notation, is exactly this kind of field. It has exactly the right transformation properties. The electromagnetic field was invented, in a sense, by the demand for local gauge invariance. Or rather, the requirement of local gauge invariance is what forces the electromagnetic field to exist. You cannot write a consistent, locally gauge invariant theory of electrons without simultaneously introducing the electromagnetic field. And the coupling between the electron field and the electromagnetic field, the coefficient that tells you how strongly they interact, is the electric charge. Charge is the coupling constant of the gauge interaction. It is the number that tells you how much the electromagnetic field has to adjust to compensate for a local phase rotation of the electron field. This is the modern understanding. Charge didn't get assigned to the electron from outside. Charge is an intrinsic consequence of what the electron is. A locally gauge invariant field, excitation, coupled to the gauge field required by that invariance, with a coupling strength that we measure and call electric charge. Emmy Noether proved in 1915 that every continuous symmetry of a physical system corresponds to a conserved quantity. This is Noether's theorem. It is one of the most important results in all of theoretical physics. If the laws of physics are invariant under time translation, meaning they work the same today as yesterday and a million years ago, then energy is conserved. If they're invariant under spatial translation, meaning they work the same here as 1 meter to the left, then momentum is conserved. If they're invariant under rotation, meaning they work the same regardless of which direction you call north, then angular momentum is conserved. And if they're invariant under global gauge transformations, meaning the physics doesn't change when you rotate the phase of the electron field by a constant angle everywhere, then something else is conserved: electric charge. The conservation of electric charge is not a law handed down arbitrarily by nature. It is a theorem. It follows mathematically from the gauge symmetry of the electron field, combined with Noether's result. Every time you observe a charged particle being created or destroyed, the total charge of everything else in the universe adjusts to compensate. A positron-electron pair can be created from two photons. The positron carries charge +1. The electron carries charge -1. Total charge created, 0. The photons had 0 charge. Total charge before, 0. Charge is conserved. This happens every time. Not because we've checked it millions of times and it always worked out. It happens because the mathematics of gauge invariance demands it. The experiment is just confirming the theorem. Now, let's be specific about the particles. The standard model of particle physics is the best description of fundamental particles and forces that has ever been constructed. It was developed through the 1960s and 70s, built by dozens of physicists, working in parallel and occasionally competing. It predicts the results of particle physics experiments with extraordinary precision, and at its core, it is a gauge theory. 3 gauge symmetries, combined into a single mathematical structure. The first is U1. U stands for unitary, and the subscript 1 means it's one-dimensional. U1 is the simplest possible gauge symmetry. It corresponds to rotations of a single phase angle, exactly the symmetry we've been discussing. The gauge field associated with U1 is the electromagnetic field. The gauge boson is the photon. The conserved charge is electric charge. The second symmetry is SU2. SU stands for special unitary. This is a more complex symmetry. SU2 has 3 generators, meaning there are 3 independent directions you can rotate in the abstract space this symmetry defines. The gauge bosons associated with SU2 are 3 particles called the W positive boson, the W negative boson, and the Z boson. The conserved charge associated with SU2 is called weak isospin. This is the symmetry responsible for the weak nuclear force, which governs processes like radioactive beta decay. In beta decay, a neutron inside an atomic nucleus converts to a proton, emitting an electron and an antineutrino. The W-negative boson is the particle that mediates this process. It carries the relevant charges from one place to another. The third symmetry is SU3. SU3 has 8 generators, 8 independent directions in its abstract symmetry space. 8 corresponding gauge bosons, called gluons. The conserved charge associated with SU3 is color charge. This is the charge of the strong nuclear force. The force that holds quarks together inside protons and neutrons, and quarks together inside every atomic nucleus, in every atom you've ever touched. The strong force is what keeps atoms from flying apart. These 3 symmetries, U1 cross SU, 2 cross SU, 3, describe all the known forces except gravity, all the matter we've ever observed, all the interactions we've ever measured. And each force arises from the same logic. Demand local gauge, Invariance. Introduce a compensating gauge field. The coupling to that field is the corresponding type of charge. The pattern repeats at each level. The mathematics is more complex for the non-abelian cases, like SU2 and SU3. But the underlying idea is identical. Charge is a coupling to a gauge field. Every type of charge is a coupling to a different gauge field. And every gauge field exists because of a demand for local symmetry. The gluons of the strong force deserve special attention because they reveal something about charge that electromagnetism hides. Gluons are the gauge bosons of SU3. But SU3 is what mathematicians call a non-abelian group. In an abelian group, the order of operations doesn't matter. Rotate by 30 degrees, then 60 degrees. Same result as 60, then 30. U1. The gauge group of electromagnetism is abelian. Photons are the gauge bosons of U1, and because U1 is abelian, photons don't carry electric charge themselves. They're electrically neutral. They mediate the electromagnetic force, but don't feel it themselves. Two beams of light can pass directly through each other without interacting. Photons interact with electrons. They don't interact directly with other photons, except at extreme energies where higher-order quantum processes become relevant. SU3 is non-abelian. The order of operations matters. Apply one SU3 transformation and then another, and the result depends on which you do first. This non-commutativity has a profound physical consequence. Gluons carry color charge. Gluons interact with other gluons. This is fundamentally different from electromagnetism. And it's why the strong force behaves so differently from anything in our everyday experience. In electromagnetism, the force between two charges weakens with distance. Two electrons repel each other. Push them apart, and the force gets weaker. This is Coulomb's law. The force falls off as 1 over the distance squared. The electric field lines spread out, and the farther apart the charges, the fewer field lines per unit area, the weaker the force. The strong force doesn't do this. The force between a quark and an antiquark doesn't weaken with distance. It stays roughly constant. The reason is that gluons attract each other. As you try to pull a quark away from an antiquark, the gluon field lines between them don't spread out. They get pulled together by gluon-gluon interactions into a tube, a string of color field. The energy stored in this string grows linearly with the distance between the quarks. Pull them a little farther apart, and a little more energy goes into the string. Pull them far enough, and the energy in the string becomes large enough to create a new quark-antiquark pair from the vacuum. The string snaps at its midpoint, creating two new particles. You never get a free quark. Every attempt to separate a quark just creates more quarks. Quarks are permanently confined inside color-neutral particles, protons and neutrons, and the hundreds of other particles built from quarks. This phenomenon is called confinement, and it is a direct consequence of color charge. Because gluons carry color charge. Because SU3 is non-abelian. Because the strong forces gauge bosons interact with each other in a way that electromagnetic gauge bosons don't. The difference between a force where charge can be separated, like electromagnetism, and a force where charge is permanently confined, like the strong force, comes down to whether the symmetry group is abelian or non-abelian, whether the force carriers carry charge themselves. The structure of the gauge group determines the behavior of the force at long distances. That's how deep the connection goes between the mathematics of symmetry and the observable physics of matter. Now, let's get specific about which particles carry which types of charge. In the Standard Model, matter particles come in two types: quarks and leptons. Quarks carry all three types of charge. They have electric charge, weak isospin charge, and color charge. Leptons carry electric charge and weak isospin, but not color charge. The electron is a lepton. It has electric charge, -1. It has weak isospin charge, but it has no color charge. This is why electrons don't interact via the strong force. No color charge means no coupling to gluons. Neutrinos are also leptons. They have weak isospin, but no electric charge and no color charge. This is why neutrinos are so difficult to detect. They don't feel the electromagnetic force. They don't feel the strong force. They only interact via the weak force, which has an extremely short range because the W and Z bosons are massive. Trillions of solar neutrinos pass through your body every second. Almost none of them interact with anything in your body. They pass through the entire Earth as if it weren't there. Not because the Earth is transparent to neutrinos in the way glass is transparent to light. Because the probability of a neutrino interacting with any given atom is vanishingly small. The weak force is, by every measure, weak. Quarks, by contrast, are saturated with charge. An up quark has electric charge, +2/3. A down quark has electric charge, -1/3. Each quark carries one of three color charges, labeled red, green, and blue, not actual colors. These labels were chosen because color mixing in this quantum context behaves mathematically like mixing primary colors of light. A red-up quark, a green-up quark, and a blue-down quark bound together form a proton. The total color of the proton is colorless, the quantum analog of mixing red, green, and blue into white. The total electric charge is +2/3, +2/3, -1/3, which equals +1. A neutron consists of two down quarks and one up quark. Charges: -1/3, -1/3, +2/3. Total electric charge: 0. That's why neutrons are electrically neutral. Not because they have no charge at all inside, but because the charges of their constituent quarks cancel. Internally, neutrons are seething with color charge and interacting gluons. It's only their electric charge that sums to 0. The Higgs field deserves its own discussion here, because it is the reason the Standard Model has the structure it does, and it changes how we should think about charge at a deeper level. Before the Higgs mechanism operates, the Standard Model has SU, 2 cross U, 1 gauge symmetry. Not the symmetries we've described separately, but a combined symmetry. In this combined, unbroken symmetry, the gauge bosons of SU2 and U1 are all massless. The Higgs field, in its lowest energy state, the vacuum state, has a non-zero value. This is called the Higgs vacuum expectation value, approximately 246 giga-electron volts. This non-zero field permeates all of space, and it breaks the SU2 cross U1 symmetry spontaneously. The original combined symmetry is replaced by a smaller symmetry, U1, electromagnetism. 3 of the original gauge bosons acquire mass through the Higgs mechanism. They become the W positive, W negative, and Z bosons. One linear combination of the original bosons remains massless. That's the photon. The breaking of the symmetry also gives masses to the quarks and charged leptons through Yukawa couplings, interactions between the fermion fields and the Higgs field. The mass of each particle is proportional to how strongly it couples to the Higgs field. The top quark, the heaviest of the quarks, couples very strongly to the Higgs field. Its mass is about 173 giga-electron-volts. The electron couples much more weakly. Its mass is about 0.511 mega-electron-volts. What matters for our story about charge is this. The Higgs field is not just about mass. It's about symmetry breaking. And symmetry breaking changes the relationships between different types of charge. Before symmetry breaking, what we'd now call electric charge and what we call weak isospin were not separate things. They were components of a single unified charge within the combined SU2 cross U1 framework. After symmetry breaking, they separate. Electric charge becomes the observable charge we measure with voltmeters. The charge you call electric charge is literally a combination, a linear superposition of 2 deeper charges from the unbroken theory. Charge, even in the standard model, is not as primitive as it looks. It depends on which phase of the Higgs field we happen to live in. Let's talk about the fine structure constant, because it is one of the strangest numbers in physics. The strength of the electromagnetic interaction is measured by a dimensionless number called the fine structure constant. It's usually written as alpha. Its value is approximately 1 divided by 137.035999, a pure number with no units. The fine structure constant determines how strongly photons couple to electrons. It determines the sizes of atoms, the energies of chemical bonds, the way light interacts with matter. If it were a little larger, atoms would be smaller and chemistry would be different. If it were much larger, atoms might not exist at all, because electrons would radiate away all their energy instantly. If it were much smaller, atoms would be huge, chemistry would be feeble, and biology as we know it would be impossible. Richard Feynman, who did more than almost anyone to develop quantum electrodynamics, called the fine structure constant one of the greatest mysteries of physics. He said that all good theoretical physicists put this number up on their wall and worry about it, because no one knows where it comes from. The standard model takes it as an input. You measure it experimentally and plug it in. The theory doesn't explain why it has the value it has. This is deeply unsatisfying. If charge is a fundamental geometric consequence of gauge invariance, why does it have this specific strength? Gauge invariance tells you that charge must exist and that it must be conserved. It doesn't tell you how strong it must be. The strength of the coupling is a free parameter. Nature had to choose a value, and nature chose 1 over 137. We don't know why. One possible hint comes from what's called the running of coupling constants. The fine structure constant is not actually fixed. It changes with energy. At low energies, everyday energies, it's approximately 1 over 137. At the energy scale of the Z boson, about 91 giga-electron volts, it's closer to 1 over 128. At higher energies still, it continues to grow. The strong coupling constant does the opposite. It decreases with increasing energy. At low energies, the strong force is enormous. At high energies, quarks behave almost like free particles. This is called asymptotic freedom, discovered by David Gross, Frank Wilczek, and David Politzer in 1973. Work that earned them the Nobel Prize in Physics in 2004. Now, here's the tantalizing part. If you extrapolate the running coupling constants of the Standard Model to very high energies, the electromagnetic coupling, the weak coupling, and the strong coupling get close to each other at energies around 10 to the 15 giga-electron volts. They don't quite meet in the minimal Standard Model. But in extensions of the Standard Model, especially supersymmetric extensions, the three couplings converge to almost exactly the same value at a single energy scale. This near convergence suggests that at extremely high energies, the three forces might be aspects of a single unified force, a single gauge symmetry with a single coupling constant. Grand unified theories attempt to make this precise. They propose that the gauge group of the Standard Model is a subgroup of a larger gauge group. SU5 is the simplest such proposal, made by Howard Georgi and Sheldon Glashow in 1974. In SU5, the quarks and leptons are unified into common multiplets. The up quarks, down quarks, electrons, and neutrinos are all related by the symmetry. And crucially, the quantization of electric charge, the fact that all charges are multiples of some smallest unit, is explained by the group theory of SU5. It becomes a theorem within the unified theory, not an experimental observation to be explained later. A logical necessity from the mathematics of the unified symmetry group. Grand unification also explains one of the most striking facts about charge, a fact so basic that most people have never stopped to find it remarkable. The charge of the proton is exactly equal and opposite to the charge of the electron, not approximately equal, not equal within our best measurement precision, with some small discrepancy hidden in the error bars. Exactly equal. Experiments have verified the equality of the proton and electron charges to better than 1 part in 10 to the 21st. That's a 1, followed by 21 zeros. This is one of the most precisely tested facts in the history of experimental physics. And it is strange when you step back, because the proton and the electron are completely different particles. The proton is made of quarks, bound together by the strong force. The electron is a fundamental particle with no internal structure. The proton is about 1,836 times heavier than the electron. They interact with completely different forces by completely different mechanisms. They arose from completely different dynamics in the early universe. And yet, their electric charges are exactly opposite. The Standard Model has no explanation for this. The Standard Model can accommodate a proton and electron whose charges don't exactly cancel. The equality is just observed. Grand unified theories do provide an explanation. In a grand unified theory, the proton and electron are related by the unified symmetry. The quantization and equality of their charges is a theorem within the unified framework. In the same way that the symmetry of a snowflake tells you that every branch must have a corresponding branch at a 60-degree rotation, the symmetry of a grand unified theory tells you that the proton and electron must have exactly opposite charges. The equality is required. The fact that charge comes in discrete units, The fact that every particle's charge is a multiple of some smallest unit would also be explained by the structure of the unifying group. Grand unified theories predict that the proton itself should occasionally decay, converting into lighter particles over timescales vastly longer than the age of the universe. The most basic prediction of minimal SU5 is that the proton should decay into a positron and a neutral pion with a lifetime of about 10 to the 30 years. Experiments have been watching for this for decades. The Super Cameo Candid detector in Japan contains 50,000 tons of ultra-pure water surrounded by 11,000 photomultiplier tubes. It has been running since 1996. After decades of observation, it has seen no proton decays. The experimental lower limit on the proton lifetime for this decay mode is now greater than 10 to the 34 years. This is already longer than the prediction of minimal SU5. Minimal SU5 is ruled out. More complex grand unified theories with higher symmetry groups make predictions for proton decay that are still consistent with current limits. The search continues. Let's talk about the quantum vacuum, because what it does to charge is both bizarre and measurable. The vacuum isn't empty. That statement deserves a moment. When physicists say the vacuum is the lowest energy state of a quantum field, they don't mean there's nothing there. They mean the fields are all in their ground states. And quantum fields in their ground states are not quiescent. They fluctuate. The uncertainty principle requires it. If a field were exactly zero everywhere, you'd know both its value and its rate of change with perfect precision simultaneously. The uncertainty principle says you cannot do that. So the vacuum field is never exactly zero. It fluctuates constantly around zero. These fluctuations manifest as virtual particle-antiparticle pairs. For the electromagnetic field, this means virtual photons. For the electron field, this means virtual electron-positron pairs. Virtual particles are not real particles in the usual sense. They don't persist. They exist for a time limited by the uncertainty principle, then annihilate. But during the brief time they exist, they interact with real particles. And this changes the effective properties of real particles. Specifically, it changes the effective electric charge. Around every real electron, there's a cloud of virtual positron-electron pairs constantly appearing and disappearing. The virtual positrons, being positively charged, are slightly attracted toward the real electron. The virtual electrons are slightly repelled. This creates a polarization of the vacuum, a region of net positive charge surrounding the real electron at very short distances, partially screening the electron's negative charge from distant observers. From far away, you don't see the full bare charge of the electron. You see the partially screened charge, reduced by the polarization cloud. This effect is called vacuum polarization. As you probe the electron at shorter distances, getting inside more and more of the polarization cloud, you start to see more of the bare charge. The effective charge increases as you probe at higher energies. This is the running of the electromagnetic coupling constant. The fine structure constant is not 1/137 at all energies. That's its low energy, long-distance value. At the scale of the Z boson, the effective charge has increased because you're probing more deeply into the electron, seeing past more of the screening. This running has been measured with exquisite precision. The results match the predictions of quantum electrodynamics to many decimal places. Vacuum polarization is real. The screening is real. The charge you call the charge of the electron is actually a running, energy-dependent, effective coupling. The bare charge, the charge of the electron without any vacuum polarization effects, is technically infinite in the absence of some higher energy cutoff. This is one of the infinities that renormalization removes from quantum electrodynamics. You absorb the infinite bare charge into the definition of the physical charge. Define the physical charge to be what you measure at low energies, and compute everything else relative to that. The results match experiment to 11 decimal places. Renormalization works. One of the strangest predictions that comes out of combining quantum mechanics with electromagnetism is the Lamb shift. In 1947, Willis Lamb and Robert Rutherford measured the energy levels of hydrogen with extraordinary precision using microwave techniques developed during the Second World War. According to the Dirac equation, two energy levels of hydrogen that have the same principal quantum number and the same total angular momentum should have the same energy. They're called the 2s1/2 state and the 2p1/2 state. The Dirac equation predicts their degenerate. Same energy. Lamb and Rutherford found they don't have the same energy. The 2s1/2 state is shifted up by about 1058 megahertz relative to the 2p1/2 state. This is the Lamb shift. The explanation was provided by Hans Bethe shortly after the measurement. The vacuum fluctuations of the electromagnetic field disturb the electron's orbit in the hydrogen atom. Virtual photons are constantly being emitted and reabsorbed by the electron as it moves in its orbital. These virtual photons shift the energy of the electron slightly by an amount that depends on the specific orbital. The s orbital, where the electron has a non-zero probability of being at the nucleus, is shifted differently than the p orbital. The Lamb shift is a direct measurement of quantum field theory, of the fact that the electromagnetic field fluctuates even in the vacuum, of the fact that the electron's charge interacts with these fluctuations. The theoretical prediction of quantum electrodynamics matches the measured Lamb shift to a precision of better than 1 part in a million. The electron's anomalous magnetic moment, another quantum electrodynamics prediction, has been measured and calculated to agree to 1 part in 10 to the 12th. That's 12 decimal places of agreement between theory and experiment. Quantum electrodynamics is the most precisely tested theory in the history of science. And every single one of its predictions involves the coupling of the electron to the electromagnetic field. The coupling we call charge. The electron is a point particle, or at least it appears to be, down to the smallest distances current experiments can probe. Those distances are around 10 to the minus 18 meters. 1,000th of a proton diameter. No internal structure has been found. No hint of substructure. The electron appears to be a mathematical point coupled to the quantum fields of the Standard Model. A point particle in classical electrodynamics has infinite self-energy. The energy stored in the electric field of a point charge, if you integrate it over all space, diverges at small distances because the field gets infinitely strong as you approach the charge. The formula for electric potential energy involves dividing by the distance from the charge, and at exactly 0 distance, you divide by 0. Infinity appears. This infinity was troubling to physicists for decades. It still appears in quantum field theory as the renormalization infinities we discussed. The ratio of the classical electron radius to the Bohr radius, which is the characteristic size of the hydrogen atom, is approximately the fine structure constant, 1/137. The fine structure constant appears everywhere in atomic physics because it's the natural coupling strength of the quantum electromagnetic interaction. It controls how strongly atoms interact with light, how fast they emit photons, how large atomic orbitals are. Everything about the interaction of light with matter depends on this one number, the number whose value remains, to this day, one of the great mysteries of physics. Let's visit something even more exotic. In certain materials, usually at very low temperatures in the presence of a very strong magnetic field, electrons can form a collective quantum state where strange things happen to charge. This is the world of the quantum Hall effect. In an ordinary conductor, if you run current through it in a magnetic field and measure the voltage perpendicular to the current, you get what's called the Hall voltage. The ratio of the Hall voltage to the current, called the Hall resistance, depends on the strength of the magnetic field and the density of charge carriers. In the 1980s, Klaus von Klitzing discovered that at low temperatures and high magnetic fields, the Hall resistance doesn't vary continuously with field strength. It takes only specific, discrete values, integer multiples of a fundamentale unit. The quantum of resistance, h divided by E squared, where h is Planck's constant and E is the electron charge. This is the integer quantum Hall effect. The Hall resistance is quantized to better than 1 part in a billion. This precision is so extreme that the quantum Hall effect is now used as the international standard for electrical resistance. The ohm, the unit of resistance, is defined in terms of the quantum Hall resistance. But the story gets stranger. In 1982, Daniel Tsui, Horst Stormer, and Arthur Gossard discovered that in samples of even higher purity, at lower temperatures in stronger fields, the Hall resistance could also be quantized at fractional values, 1/3 of the fundamental unit, 2/5, 3/7, other fractions. This is the fractional quantum Hall effect, and it's explained by something remarkable. At these extreme conditions, the electrons form a collective quantum state, a new phase of matter, where the elementary excitations are not individual electrons. They are quasi-particles, collective oscillations of the entire many-electron system that behave in many ways like independent particles. And crucially, these quasi-particles carry fractional electric charge, 1/3 of the electron charge, or 1/5, or other fractions, corresponding to the specific quantum Hall state. These are not violations of charge quantization. The individual electrons still each carry exactly -1 unit of electric charge. But the collective behavior of many electrons interacting in a strong magnetic field creates emergent objects that behave exactly as if they carry fractional charge. This was confirmed experimentally. The fractional charge of quasi-particles in the 1/3 quantum Hall state has been measured directly using very sensitive noise measurements. It is 1/3 of the electron charge. Tsui, Stormer, and Laughlin, who provided the theoretical explanation, won the Nobel Prize in Physics in 1998. The fractional quantum Hall effect shows that charge, while quantized at the fundamental particle level, can manifest in fractional values at the collective level. Emergence creates new, effective types of charge from many ordinary charges. The behavior of the collective is richer than the behavior of the individual parts. Now, magnetic monopoles deserve our attention because their absence tells us something profound about the structure of charge. Maxwell's equations for the electromagnetic field are not symmetric between electricity and magnetism. On the electric side, you have electric charges, point sources of electric field. Positive charges create field lines pointing outward. Negative charges create field lines pointing inward. On the magnetic side, there are no magnetic charges, no magnetic monopoles. Every magnetic object you've ever encountered has two poles, north and south. There are no objects with only a north pole and no south pole anywhere in nature. If you cut a bar magnet in half, you don't get a north-only piece and a south-only piece. You get two smaller bar magnets, each with a north and a south. The absence of magnetic monopoles is built into Maxwell's equations. One of the equations, Gauss's law for magnetism, simply states that there are no sources or sinks of magnetic field anywhere. No monopoles. But this is not a derivation from first principles. It's an assumption encoded in the equation because no one had ever observed a magnetic monopole. In 1931, Paul Dirac showed that if magnetic monopoles existed, they would explain something that the current theory doesn't explain: the quantization of electric charge. The quantization condition that Dirac derived relates the product of the electric charge and the magnetic charge to a multiple of Planck's constant divided by 2 pi. If even one magnetic monopole exists somewhere in the universe, then the consistency of quantum mechanics requires that all electric charges be quantized. All electric charges must come in discrete integer multiples of some fundamental unit. The quantization of charge would be explained. Grand unified theories predict that magnetic monopoles should have been produced abundantly in the very early universe. They would have a mass around 10 to the 16 giga-electronvolts. Cosmological inflation, the period of exponential expansion in the very early universe, would have diluted any monopoles to densities too low to detect. So monopoles may exist, just extremely rarely. There have been claims of monopole detection over the decades. In 1982, Blas Cabrera reported a single event in his monopole detector that was consistent with a monopole passing through. The event was never repeated. No other monopole detector has ever seen a convincing signal. The search continues. If a magnetic monopole is ever detected, the quantization of electric charge would have a natural explanation. And the connection between charge and topology, between the structure of gauge fields and the global properties of space, would be confirmed at a new level. Now, let's think carefully about where charge lives in space. If you ask where the mass of an electron is, there's a sensible answer. It's where the electron is. The electron is a localized excitation of the electron field. When you detect an electron at a particular location, you find its mass there. But where is the charge? The charge of the electron isn't purely localized at the electron. Part of the story of electric charge is that it affects the electromagnetic field everywhere. An electron creates an electric field that extends throughout all of space. Not just near the electron. Everywhere. Infinitely far away. That electric field carries energy. It carries momentum. It even carries angular momentum in some configurations. The total energy of an electron isn't just the mass energy. It includes all the energy in the electric field spread across all of space. This is part of why the self-energy problem was such a crisis in early quantum field theory. The energy stored in the Coulomb field of a point charge, if you integrate over all space, diverges. At small distances, because the field gets stronger as you approach a point charge. At large distances, the divergence is handled differently. The universe is electrically neutral overall. The universe has equal amounts of positive and negative charge. Total charge is 0. And that fact, that the universe as a whole carries no net electric charge, is not a coincidence. It's likely a consequence of the same symmetry principles. In the hot, dense, early universe, particle physics processes would have enforced charge neutrality. For every charged particle produced, the conservation of charge requires an equal and opposite charge somewhere else. If the universe began in a state of zero charge, gauge invariance guarantees it stayed that way. The electromagnetic fields of all the charges in the universe largely cancel each other over large distances, leaving local concentrations where charges are imbalanced, but zero net effect at cosmological scales. Now let's consider the relationship between charge and antimatter. We said that the positron is the antiparticle of the electron with opposite charge. This is general. Every particle in the standard model has a corresponding antiparticle with opposite charges but identical mass. The antiproton has charge -1. Anti-up quarks have charge -2/3. Anti-down quarks have charge +1/3. This isn't a coincidence. It's a consequence of a theorem called the CPT theorem. CPT stands for charge conjugation, parity reversal, and time reversal. Charge conjugation means flipping the signs of all charges. Parity reversal means reflecting the spatial coordinates through a point, like looking at the universe in a mirror. Time reversal means reversing the direction of time. The CPT theorem states that any relativistic quantum field theory that is Lorentz invariant must be symmetric under the combined operation of applying all three of these simultaneously. This theorem is extraordinarily well tested. No violation of CPT symmetry has ever been observed. One consequence is that for every particle, there must exist an antiparticle with opposite charge but identical mass and spin. The electron has mass 0.51, 1 megaelectronvolts, and charge -1. The positron has mass 0.511 megaelectronvolts and charge +1. The masses must be exactly equal. Experiments have measured the masses of the electron and positron to agree to better than 1 part in 10 to the 8th. If there were any difference, it would violate CPT symmetry and shake the foundations of quantum field theory. So the two signs of charge are not an arbitrary choice. They are a consequence of combining gauge symmetry with the requirements of relativistic quantum mechanics. If you want a consistent quantum field theory in a universe where special relativity holds, charges must come in two signs. That's not negotiable. The universe contains mostly matter and very little antimatter. This is one of the deepest unsolved mysteries in physics. The laws of physics, as we understand them, treat matter and antimatter nearly symmetrically. CPT symmetry is exact. CP symmetry, charge conjugation combined with parity, is violated in certain weak interactions. This CP violation was discovered in 1964 by James Cronin and Val Fitch, work that earned them the Nobel Prize in Physics in 1980. The violation of CP symmetry means the laws of physics are not perfectly symmetric between matter and antimatter. There's a slight asymmetry. One of the three conditions required for the universe to end up matter-dominated, as identified by physicist Andrei Sakharov in 1967, is precisely this CP violation. But the CP violation in the Standard Model is far too small to explain the observed matter-antimatter asymmetry. The universe contains roughly 1 billion times more photons than baryons, the class of particles that includes protons and neutrons. This ratio reflects the tiny excess of matter over antimatter that survived after most matter and antimatter annihilated in the early universe. Getting from exactly equal amounts of matter and antimatter at the start to this ratio requires much more CP violation than the standard model provides. Something else must have violated CP symmetry more strongly in the early universe. New physics. Physics beyond the standard model. The asymmetry between matter and antimatter is an asymmetry in how charge is distributed across the universe. More particles with charge -1 than particles with charge +1. More particles with charge positive 2/3 than particles with charge negative 2/3. The net charge is 0. It must be. But the matter-antimatter asymmetry tells us something very specific about which particles carry which charges, and explaining that asymmetry might reveal entirely new types of charge symmetry violation that we haven't yet discovered. At this point, you might be wondering about gravity. We've talked about electric charge, color charge, weak isospin. Some physicists informally call mass the gravitational charge. The reasoning is that mass plays the same role in gravity that electric charge plays in electromagnetism. Mass is what couples to the gravitational field. More mass means stronger gravitational attraction, the same way more electric charge means stronger electromagnetic attraction. And, if gravity is a gauge theory, which general relativity can be written in a way that makes it look somewhat like one, then mass is the conserved quantity associated with the gauge symmetry of general relativity. But gravity is different from the other forces in a crucial way. In electromagnetism, you have positive and negative charge. The force between opposite charges is attractive. The force between like charges is repulsive. This gives electromagnetism a kind of balance, a way for large collections of matter to be electrically neutral by mixing positive and negative charges. In gravity, there is no negative mass. Every particle with mass produces attractive gravity. There's no cancellation, no shielding, no way to combine two objects to make something with zero gravitational effect. This is why, at large scales, gravity dominates. Electric forces are locally enormous, but over large distances they cancel because matter is electrically neutral. Gravity never cancels. It just accumulates. And this is why galaxies form, why stars collapse, why the large-scale structure of the universe is governed by gravity, even though gravity is by far the weakest of the fundamental forces. Measuring in terms of force between two protons at a given distance, gravity is about 10 to the 36 times weaker than electromagnetism. And yet, gravity determines the fate of the cosmos. Because electric charge cancels. Because gravitational charge doesn't. The asymmetry of gravitational charge, the fact that it only comes in one sign, is what allows the universe to develop structure on the largest scales. There is also the question of charge and quantum gravity, where our current knowledge has hard limits. We have two extraordinarily successful theories. Quantum field theory, which describes the subatomic world with 11 decimal places of precision, and general relativity, which describes gravity and the large-scale structure of the universe with extraordinary precision. These two theories are incompatible with each other. They cannot both be correct in the regime where both quantum mechanics and strong gravity matter simultaneously. The regime inside black holes. The first moments after the Big Bang. At those extremes, both theories make contradictory predictions. We need a theory of quantum gravity To resolve the contradiction, we don't have one. String theory is the leading candidate. In string theory, the fundamental objects are not point particles, but one-dimensional strings of energy. Different vibrational modes of these strings correspond to different particles. String theory naturally incorporates gauge symmetries. In fact, gauge symmetries emerge from the geometry of the extra dimensions that string theory requires. The different types of charge, the coupling constants of the different gauge interactions, are related to the shapes and sizes of the extra dimensions. If string theory is correct, then the fact that the fine structure constant is 1/137 and not some other number reflects the specific geometry of the extra dimensions in our universe. The geometry of dimensions too small to observe, rolled up into spaces so tiny that they're effectively invisible at the energies we can reach. But determining that geometry, understanding why our universe chose this particular compactification and not another, remains one of the deepest unsolved problems. Loop quantum gravity is another approach to quantum gravity. It quantizes space-time itself, makes space come in discrete chunks, like pixels, at the Planck length of about 1.6 times 10 to the minus 35 meters. In loop quantum gravity, the behavior of charge at those scales might be fundamentally different from anything we currently predict. The electromagnetic field might be quantized in units determined by the discrete geometry of spacetime. Whether these speculative frameworks will eventually explain the value of the fine structure constant, or the quantization of charge, or the matter-antimatter asymmetry, remains to be seen. These are genuine frontiers where physics hasn't yet found its footing. Now, there is one more dimension to the nature of charge that connects everything we've discussed and points toward the deepest question of all. What is it about the mathematics of the universe that makes gauge symmetry the right framework? Why do quantum fields obey gauge invariance? We've explained charge in terms of gauge invariance, but we haven't explained gauge invariance. What forces the universe's equations to have this property? The most honest answer is, we observe that they do. Every experiment ever performed is consistent with gauge invariance. The predictions of gauge theories match all observations. But we don't have a deeper explanation for why gauge invariance must hold. One perspective is that gauge invariance isn't really a symmetry in the usual sense. A true symmetry relates two different physical situations that look the same, but a gauge transformation doesn't relate two different physical situations. It relates two different mathematical descriptions of the same physical situation. The electromagnetic gauge transformation changes the potential field, but it doesn't change anything observable, because the potential isn't directly observable. Only the electric and magnetic fields are observable, and the electric and magnetic fields don't change under a gauge transformation. From this perspective, gauge invariance is not a symmetry of nature. It's a redundancy in our mathematical description. The fact that we can describe the same physics using different potentials, gauge invariance is saying, our formalism has too much freedom. We need to pick a particular gauge to make calculations tractable. But the physical results must not depend on which gauge we pick. If that's the right perspective, then the question of why gauge invariance holds becomes, why is our mathematical description of electromagnetism redundant? And the answer might be that any consistent description of a massless spin-1 particle, which is what the photon is, necessarily has this redundancy built in. There's a theorem that says a massless spin-1 particle must couple to a conserved current. And the conserved current means there's a conserved charge. The photon must mediate a force associated with a conserved charge. The photon couldn't exist without charge being conserved. Charge conservation isn't imposed on electromagnetism from outside. It's woven into the fabric of what it means for a massless spin-1 particle to exist. If you want photons, you must have charge. You don't get to choose. We've come a long way from that battery in your drawer. But the chain of logic is unbroken. The electron couples to the electromagnetic field. That coupling is charge. The coupling exists because the equations describing the electron field must be invariant under local phase transformations. Local gauge invariance requires the electromagnetic field. The conservation of charge is a theorem that follows from Noether's theorem applied to gauge symmetry. The specific value of the coupling, 1/137 at low energies, is measured but not derived by the Standard Model. The Standard Model itself, all of it, is a gauge theory based on 3 local symmetries. All the forces arise from the same logic, the same demand for local consistency, the same mathematical structure. At higher energies, these 3 symmetries might be unified into one, explaining why the different charges have the specific values they do, why the proton and electron charges are exactly equal and opposite, why charge is quantized. All of it connected, all of it following from a single deep demand, that the physics not depend on the arbitrary choice of phase at each point in space. Charge is the price of that demand, and the forces of nature are the payment. Now, none of this resolves every mystery. Far from it. We still don't know why the electron has the specific mass it has. We don't know why the fine structure constant has the value it has. We don't have a theory that unifies quantum field theory with general relativity. We don't know whether the proton and electron charges being exactly equal is a consequence of some deeper unification. We don't know what dark matter is, or whether it carries its own type of charge under some new symmetry. We don't know why there is more matter than antimatter in the universe, even though the laws of physics treat them nearly symmetrically. Charge conservation guarantees equal and opposite charges were produced in the early universe. And yet, here we are, made of matter, surrounded by matter. Something broke the symmetry enough to create the imbalance we inhabit. We don't know what that something was. These are open questions. Real, deep, unsolved problems in fundamental physics. And the answers, when they come, will almost certainly involve new symmetries, new gauge fields, new types of charge that we haven't yet detected. Because that's the pattern. Every time physicists have found a new conserved quantity, a new pattern in particle interactions, a new mystery that existing theories couldn't explain, the answer has been a new symmetry, a new gauge invariance, a new field, a new type of charge. Electromagnetism was unified with the weak force in the electroweak theory of Glashow, Salem, and Weinberg, earning them the Nobel Prize in Physics in 1979. 2 seemingly separate forces with different types of charge turned out to be aspects of one combined gauge symmetry, broken by the Higgs field. The same unification might be waiting at higher energies, connecting all known forces. The pattern shows no signs of stopping. The universe is not made of things. It is made of relationships, of symmetries and their consequences, of fields and their excitations, of conservation laws that are theorems, not rules. The electron you move through a wire is not a tiny marble with a property called charge glued onto it. It is a disturbance in a field that spans the entire cosmos. And its charge is not a label. It is the depth of the coupling between that disturbance and the field that had to exist because of a demand for mathematical consistency. The next time you flip a light switch, you're activating one of the most precisely understood phenomena in all of science. Electrons coupling to photons through a gauge field that had to exist because the universe's equations for electrons must be invariant under local phase rotations. A field required by symmetry. A coupling we call charge. A conservation law that is not a rule but a theorem. And the light that fills the room is proof that mathematics, at its deepest level, is not abstract. The light is the universe enforcing its own internal consistency. And we get to see by it. Let's step back and think about what it means to describe something as fundamental. In everyday language, when we say a property is fundamental, we mean it can't be broken down further. It's a primitive, a bedrock fact. The color of a sweater is not fundamental. It arises from the specific dye molecules and how they absorb and reflect different wavelengths of light. The temperature of a gas is not fundamental. It's the average kinetic energy of the molecules making up the gas, emergent from motion at a deeper level. The question is whether electric charge is like color or temperature, emerging from something deeper, or whether it's truly primitive. And the answer quantum field theory gives is both and neither. Charge is not made of smaller components. You cannot split the charge of an electron into parts. You cannot find the internal machinery that produces it. In that sense, it is primitive. But it is not primitive in the sense of being arbitrary. It doesn't exist because someone decided electrons should have charge. It exists because a consistent mathematical description of a field, like the electron field, in a relativistic universe, cannot avoid coupling to a gauge field. The charge is a consequence, a theorem. It's as inevitable as the conservation of energy. This puts charge in a strange philosophical category. It's not reducible to simpler constituents, but it's also not arbitrary. It's necessary, logically required by the structure of the theory. The electron couldn't not have charge, given the kind of particle it is. This is different from, say, the electron's mass. Gauge invariance demands that charge exist and that it be conserved. Gauge invariance says nothing about the mass. The electron's mass is a free parameter in the Standard Model, set by the Yukawa coupling to the Higgs field. That coupling could, in principle, have any value. We measure it. But the electron's charge, in principle, could only be zero or non-zero. And once you decide the electron couples to the electromagnetic gauge field, it's non-zero. The actual numerical value of the coupling, 1/137, is still a free parameter. But the existence of the coupling is not. The symmetry demands it. There's a historical episode that illustrates beautifully how deeply charge is connected to the fabric of space and time. In 1918, Hermann Weyl published a paper attempting to unify gravity and electromagnetism. He was inspired by Einstein's general relativity, which described gravity as curvature of spacetime, Weyl thought. If spacetime can be curved, maybe its scale, the ruler you use to measure distances, could also vary from point to point. He proposed that the laws of physics should be invariant under changes of scale, called Weyl rescalings. At each point in space, you could rescale all lengths by a different factor. To make the equations invariant, he needed to introduce a new field, a vector field that tracked how the scale changed from point to point. He identified this field with the electromagnetic potential. Einstein objected immediately. He pointed out that if scales varied from point to point, the frequency of atomic emission lines would depend on the history of the atom. Two atoms of the same element in different places would emit different frequencies. Spectral lines would be smeared out. This was not observed. Weyl's proposal was wrong. But here's the remarkable part. When quantum mechanics arrived, Weyl revisited his idea. In quantum mechanics, the relevant quantity isn't the length scale. It's the phase of the wave function. Weyl's original insight, that local freedom in some abstract mathematical parameter requires introducing a compensating field, was right. He just had the wrong parameter. The right parameter is the phase of the quantum wave function. Weyl himself recognized this in 1929 and formulated what we now call gauge invariance in the quantum mechanical context. The word gauge, from the German word for calibration, stuck. Weyl's failed attempt to explain gravity and electromagnetism using scale invariance accidentally pointed the way to the correct understanding of where electromagnetism comes from. The wrong theory, pursued carefully and rigorously, led to the right insight. This is not unusual in physics. The most profound insights often emerge from the careful analysis of what went wrong with a wrong idea. Let me explain something about quantum electrodynamics that often gets glossed over. When physicists compute predictions, they use a technique called perturbation theory. The idea is that the coupling constant, the fine structure constant, is small, approximately 1 divided by 137. Since this is much less than 1, you can write the answer as a series. The leading term is the 0th order approximation. Each successive term adds corrections involving higher powers of the coupling constant. The first correction involves 1 power of the fine structure constant. The second correction involves 2 powers, and so on. For quantum electrodynamics, the leading term gives you the Coulomb force, the basic attraction and repulsion between charges. The first correction, proportional to 1 divided by 137, gives you the anomalous magnetic moment of the electron, the tiny deviation from the value predicted by the Dirac equation. This has been calculated to 5 loops in perturbation theory, 5 levels of quantum corrections. Each level involves calculating an enormous number of Feynman diagrams. At the 1-loop level, there is 1 diagram contributing. At the 2-loop level, there are 7 diagrams. At the 3-loop level, there are 72 diagrams. At the 4-loop level, there are 891 diagrams. At the 5-loop level, there are 12,672 diagrams. Each diagram corresponds to a specific mathematical integral that has to be evaluated. Some of them require months of computation on modern computers. The total prediction for the electron anomalous magnetic moment, after adding up all 12,672 5-loop diagrams and their contributions, agrees with the measured value to 10 decimal places, 1 part in 10 to the 10th. The measurement itself, done by trapping single electrons in a magnetic field and measuring their spin precession frequency with extraordinary precision, is one of the greatest achievements of experimental physics. This level of agreement between theory and experiment is unprecedented in the history of science. It validates not just the framework of quantum electrodynamics. It validates the coupling constant alpha, the fine structure constant. It validates the idea that charge is a coupling and that you can compute its effects perturbatively. It validates the entire mathematical machinery of gauge theory. Now, let's think about something that happens at very high energies and very short distances that changes the picture in a fundamental way. At the energies of the Large Hadron Collider in Geneva, Switzerland, the highest energy particle accelerator ever built, protons are accelerated to energies of up to 6.8 tera-electron volts each. When two protons collide at these energies, they're not just bumping two balls together. The collision is happening at such short distances that the quarks and gluons inside the protons are the things actually interacting. The proton is not a simple object. It's a complex, dynamical system. Inside a proton, at any given instant, there are two up quarks and one down quark, the valence quarks. But there are also a sea of virtual quark-antiquark pairs constantly appearing and annihilating, and gluons carrying the color force between all of them. At low energies, the proton looks like a simple object with charge +1. At high energies, probing short distances, you start to see the internal structure. You see quarks with fractional charges. You see gluons with color charge. You see the complexity hidden inside what looks like a simple charged particle. The charge you assign to the proton depends on what scale you're probing it at. At low energies, the proton has electric charge, +1. That's the net charge, the observable you measure from far away. At high energies, you're interacting with individual quarks, each carrying a fraction of the proton's charge. At even higher energies, you'd be interacting with individual quarks at shorter and shorter distances, and the effective color coupling would be getting weaker due to asymptotic freedom. The same proton, described at different scales, looks very different. This scale dependence is central to modern particle physics. It's why calculations at the Large Hadron Collider require knowing the distribution of quarks and gluons inside the proton at the relevant energy scale. The Parton distribution functions, as they're called. Enormous calculations using data from decades of collider experiments. The proton is not a simple thing, and neither is its charge. The +1 you write in a table is the net, long-distance, low-energy, effective charge. The reality inside is a swirling sea of fractional charges, color charges, gluon-gluon interactions, and quantum fluctuations. The Aharonov-Bohm effect is one of the most striking demonstrations that charge is not just about forces between particles. It's about the structure of the electromagnetic field, even in regions where there is no field at all. In 1959, Yakir Aharonov and David Bohm predicted the following. Take a long, thin solenoid, a coil of wire carrying current so tightly wound that the magnetic field is entirely confined inside it. Outside the solenoid, the magnetic field is essentially zero. Now, send an electron beam around the solenoid, splitting it into two beams that pass on either side, then recombine on the other side. The two beams interfere. You observe a pattern of bright and dark fringes. Now, turn on the current in the solenoid. The magnetic field inside the solenoid increases. Outside, where the electrons travel, the magnetic field is still essentially zero. The electrons never pass through a region with magnetic field. And yet, the interference pattern shifts. The fringes move. The electrons, traveling through regions of zero magnetic field are affected by the solenoid. This is the Aharonov-Bohm effect. It was experimentally confirmed by Akira Tonomura and colleagues in 1986 using an electron microscope and a superconducting solenoid. The effect is real. What's happening? The electrons are not affected by the magnetic field directly. They're affected by the electromagnetic potential. The potential exists outside the solenoid even when the field is zero. The potential is not a mathematical fiction. It has physical reality, even in regions where the field it generates is zero. The phase of the electron's wave function is affected by the potential along its path. The two beams take different paths. They pick up different phases from the potential. When they recombine, the phase difference causes the interference pattern to shift. This is one of the deepest demonstrations that quantum mechanics, combined with electromagnetism, contains structure that classical electromagnetism doesn't. In classical physics, what matters is the force. The potential is just a convenient computational tool. In quantum mechanics, the potential is physically real. It affects the phase of the wave function, and the phase determines interference patterns. The Aharonov-Bohm effect means that charge doesn't just couple to the electromagnetic force in regions where the force is non-zero. It couples to the electromagnetic potential globally. The electron is sensitive to what the electromagnetic field is doing everywhere, even in places the electron never visits. This is deeply quantum mechanical. There is no classical analog, and it reinforces the idea that charge is about a global coupling between fields, not just a local sensitivity to forces. Let's think about what would happen in a universe with a different type of charge. Not negative and positive charge balanced around zero, but some other structure. Complex charge, for example. What if particles could have charge in two independent directions? A complex number has a real part and an imaginary part. A charge with two independent components. You can rotate the complex number in the complex plane. This gives you a symmetry group with two generators instead of one. This is exactly the SU2 gauge symmetry of the weak force. The weak isospin charge has exactly this structure. Two independent components. An isospin up and an isospin down. Electrons have isospin minus 1/2. Neutrinos have isospin plus 1/2. They're two components of a single doublet under SU2. The gauge bosons of SU2, the W bosons, can convert electrons into neutrinos and vice versa. They can transform one component of the doublet into the other. This is completely different from photons, which cannot change the identity of a particle. A photon can push an electron around. It cannot change an electron into a neutrino. The W boson can. The reason is the richer structure of SU2 compared to U1. In U1, particles just have a single charge number. Photons can add or subtract momentum and energy. They can push particles around, but they cannot change which multiplet a particle belongs to. In SU, two particles are arranged in doublets. The gauge bosons can rotate within the doublet. Convert one particle type into another. The W positive boson, emitted in beta decay, converts a down quark into an up quark, changes the quark's flavor, changes the charge by 1 unit. This conversion is only possible because weak isospin has this two-component structure, because SU2 has the right mathematical properties to mix the components. The richness of the weak interaction, the fact that it can change particle identities, follows from the group structure of its gauge symmetry. It follows from the specific mathematical structure of the type of charge that couples to the weak force. One of the most beautiful things about gauge theory is that it predicts the existence of particles before they're observed. Maxwell's equations predicted the existence of electromagnetic waves, and hence photons, before the photoelectric effect confirmed the particle nature of light. The gauge structure of SU2 predicted the existence of the W and Z bosons before they were observed. The Standard Model, fully formulated in the early 1970s, predicted the W boson mass should be about 80 giga-electron volts, and the Z boson mass should be about 91 giga-electron volts, based purely on the gauge structure and the Higgs mechanism. The W boson was discovered in 1983 at CERN, the European Particle Physics Laboratory, in Geneva. Its measured mass, approximately 80.3 giga-electron volts. The Z boson was also discovered in 1983. Its measured mass, approximately 91.2 giga-electron volts, exactly as predicted. Carlo Rubbia and Simon Vandermeer received the Nobel Prize in Physics in 1984 for this discovery. The predictions were confirmed to better than 1%. This is the predictive power of gauge theory. It doesn't just describe what we already know. It tells us what must exist because of the symmetry structure. The gluon was predicted in exactly the same way. The SU3 gauge symmetry of the strong force requires 8 massless gauge bosons. Gluons were inferred from indirect effects long before the first direct evidence for them, from jet events in electron-positron colliders in 1979. The gauge principle is a machine for predicting new particles and interactions. You specify the symmetry group. You work out the gauge bosons. You know what interactions exist. You look for those interactions in experiments. The predictions follow from the mathematics of symmetry, from the mathematical structure of charge. Let's revisit the question of mass and charge from a slightly different angle. In the Standard Model, photons are massless. This is not accidental. It is required by gauge invariance. A mass term for the photon in the Lagrangian, the mathematical object that encodes the dynamics of the theory, is not gauge invariant. If you try to add it, the equations become inconsistent. The gauge symmetry prevents the photon from having mass. The consequence is that the electromagnetic force has infinite range. The Coulomb force between two charges falls off as 1 over the distance squared, but it never reaches 0. No matter how far apart two charges are, they still attract or repel each other. This infinite range is a direct consequence of the photon being massless, which is a direct consequence of gauge invariance. The W and Z bosons, by contrast, are massive, very massive, about 80 to 90 times heavier than a proton. This is because the Higgs mechanism spontaneously breaks the SU2 cross U1 symmetry. The W and Z bosons acquire mass through their interaction with the Higgs field. Massive gauge bosons mediate a short-range force. The range of a force mediated by a massive particle is inversely proportional to the particle's mass. The W and Z bosons, being so massive, give the weak force a range of about 10 to the minus 17 meters, 1/1000th of a proton diameter. The weak force is confined to the atomic nucleus and below. This is why radioactive beta decay, which proceeds through the weak force, has such a tiny rate compared to electromagnetic processes. The W boson has to be produced as a virtual particle, and its large mass suppresses the probability of that happening. So the range of a force, how far it extends through space, depends on the mass of its gauge bosons, which depends on whether the relevant symmetry is broken by the Higgs field, which depends on the structure of the Higgs coupling to those gauge bosons. All of these properties, force range, symmetry breaking pattern, particle masses, are encoded in the structure of the gauge symmetry and the Higgs mechanism. Charge determines what force acts. The gauge group determines the force's gauge bosons. The Higgs mechanism determines their masses. Their masses determine the range of the force. Everything connected. The precision of the Standard Model's predictions deserves one more emphasis. The anomalous magnetic moment of the muon, the heavier cousin of the electron, has been at the center of one of the most closely watched tensions in physics. The muon G-2 experiment at Fermilab, the Fermi National Accelerator Laboratory in Batavia, Illinois, completed its final measurement in 2025, reaching a precision of 127 parts per billion. When that experimental result is compared against the older data-driven theoretical prediction, the discrepancy is more than 4 standard deviations. That is close to the 5 sigma threshold physicists use to claim a discovery, and it has been taken very seriously as a possible sign of new physics beyond the Standard Model. But a competing theoretical calculation, using a technique called lattice quantum chromodynamics, that computes the contribution of the strong force from first principles rather than from experimental data, finds a result that agrees with the Fermilab measurement. The two theoretical approaches disagree with each other more than they each disagree with the experiment. So the situation is genuinely unresolved. Either the data-driven prediction contains a systematic error, or the lattice calculation does, or the experiment is seeing something real that neither theory correctly captures. New types of charge that we haven't discovered yet remain a live possibility. The story of charge is not finished. Let's think about something that most people never encounter: the concept of dual descriptions of the same physics. In quantum electrodynamics, the electric charge and the magnetic charge are related by what's called electromagnetic duality. If you take Maxwell's equations and replace the electric field with the magnetic field, and the magnetic field with the negative electric field, and replace the electric charge with the magnetic charge, and vice versa, the equations don't change. The physics is symmetric between electricity and magnetism when both types of charge are present. This is a deep symmetry, and it suggests that electric charge and magnetic charge might be related in a way we don't yet fully understand. In string theory, this duality is made precise. There are extended objects in string theory called D-branes, on which open strings can end. D-branes carry charges. Some carry electric-type charges under gauge fields. Others carry magnetic-type charges, analogous to magnetic monopoles. The two types of charges are related by the duality symmetry. S-duality, in string theory, relates a theory with strong coupling to a theory with weak coupling, and it exchanges electric and magnetic charges. A theory with weakly charged electric particles and strongly charged magnetic monopoles is dual to a theory with strongly charged electric particles and weakly charged magnetic monopoles. They're the same theory, described from different perspectives. If S-duality holds, it means that electric charge and magnetic charge are not independently defined. They're two aspects of a single underlying structure. The strength of the electric coupling and the strength of the magnetic coupling are inversely related. If the electromagnetic coupling is small, meaning charge is weak, the magnetic coupling is large. If the electromagnetic coupling is large, the magnetic coupling is small. This has implications for understanding what happens at high energies where the electromagnetic coupling grows. At strong coupling, the perturbative description using Feynman diagrams breaks down. But the dual description, in terms of magnetic charges, might be weakly coupled and tractable. Electric-magnetic duality, if fully understood, would give us two complementary windows into the same physics. Two ways of thinking about charge that are both valid and together provide a complete picture. This is still an active research area. The mathematics is under development, but the conceptual implication is striking. Electric charge and magnetic charge, which we usually think of as completely separate concepts, might be dual descriptions of the same underlying structure. Let me say something about what happens when charge meets topology. Topology is the branch of mathematics that studies properties of spaces that don't change under continuous deformation. A coffee cup and a donut are topologically equivalent. You can continuously deform one into the other without tearing. A sphere is not topologically equivalent to a donut. You cannot deform a sphere into a donut without tearing a hole in it. Topology enters the physics of charge in a beautiful way. The magnetic vector potential, the field introduced to compensate for local gauge transformations, can be non-zero even when the magnetic field is zero. This is what happens in the Aharonov-Bohm effect. The potential exists even outside the solenoid, where the field vanishes. The global structure of the potential, its topology, has physical consequences even when its local value seems irrelevant. Topological defects, regions where the structure of the gauge field cannot be smoothly deformed away, carry quantized charges. This is the origin of magnetic monopoles. A monopole is a topological defect in the gauge field. Its existence is related to the global structure of the gauge field, not just its local value. In certain gauge theories, topological defects called instantons, vortices, and monopoles are responsible for important physical phenomena. In quantum chromodynamics, the gauge theory of the strong force, instantons contribute to the violation of an approximate symmetry called chiral symmetry. This symmetry breaking gives pions their small but non-zero mass. It affects the structure of the proton. It's part of why chemistry works the way it does. Topology and charge are intertwined at a fundamental level. The structure of charge is not just about local field strengths. It's about the global architecture of the gauge fields, about how they wrap around space, about topological invariance that cannot be changed by any local process. There is something philosophically remarkable about all of this. Physicists often draw a distinction between contingent facts and necessary facts. A contingent fact is one that happens to be true, but could have been otherwise. The Earth is at a certain distance from the Sun. That's contingent. Move the Earth, and the fact changes. A necessary fact is one that couldn't have been otherwise, given the constraints. Mathematical truths are necessary. 2 + 2 = 4 in any consistent system of arithmetic. Electric charge, it turns out, is necessary in a sense that most physical features aren't. Given the existence of the electron field, given special relativity, given the basic requirements of quantum mechanics, given the demand for local gauge invariance, the electromagnetic field must exist. Charge must be conserved. The two signs of charge must exist. These are not contingent facts about this particular universe. They are necessary consequences of the mathematical structure of a consistent theory. You could imagine a universe where the electron has a different mass. The Standard Model allows any mass. You could imagine a universe where the fine structure constant has a different value. The standard model allows any coupling strength, but you cannot imagine a universe where the electron field exists. Quantum mechanics holds, special relativity holds, local gauge invariance holds. An electric charge doesn't exist. That universe would be mathematically inconsistent. The existence of charge is not a contingent fact. It's a theorem. It follows from the structure of the theory, the same way theorems follow from axioms in mathematics. This is deeply different from what most people assume when they think about why the world is the way it is. Most people assume the properties of particles are just the way they happen to be. Electrons happen to have negative charge. Protons happen to have positive charge. It could have been otherwise. The answer from quantum field theory is no. Given the type of particle an electron is, given the mathematical structure of the laws of physics, the electron must have charge. It couldn't not have it. The universe's most familiar electrical phenomenon is logically inevitable. Now, let's address something that seems simple but becomes strange quickly. When we say an electron has charge -1, what units are we using? The answer is, we're using a unit called the elementary charge. The elementary charge is approximately 1.6 times 10 to the minus 19 coulombs. The coulomb, named after Charles Augustin de Coulomb, who quantified the electric force in the 18th century, is the standard unit of charge. 1 coulomb is approximately 6.2 times 10 to the 18th elementary charges. A current of 1 ampere, the unit your circuit breakers measure in, corresponds to 1 coulomb of charge flowing past a point per second. That's 6.2 times 10 to the 18th electrons per second. Roughly 6 billion electrons. Every second. Through a wire that might be thinner than your finger. Each electron moving perhaps a millimeter per second in the drift velocity sense. But the signal, the electromagnetic wave in the field, propagating near the speed of light, charge, current, fields, waves, all happening simultaneously, all governed by gauge invariance. The coulomb is a practical unit, defined in terms of macroscopic electrical measurements. But the natural unit of charge in particle physics is the elementary charge, 1 unit. The charge of the electron is -1 elementary charge. The charge of the proton is +1 elementary charge. The charge of the up quark is +2/3 of an elementary charge. The fact that all observed particles carry charges that are integer or simple fraction multiples of the elementary charge is charge quantization. And as we discussed, charge quantization is likely a consequence of grand unification, or possibly the existence of magnetic monopoles. Either way, it's not an accident. The universe chose to make charge come in discrete units, not continuously, discrete, like the pixels of a photograph. You can't have half a pixel. You can't have half an elementary charge of a free particle. The discreteness is built in. There's a technical subtlety about charge that comes up in the context of the strong force. Quarks carry color charge, as we discussed. But color charge is different from electric charge in a way that often confuses people at first. Electric charge comes in 2 types, positive and negative. Color charge comes in 3 types, red, green, and blue, and their anti-particle versions, anti-red, anti-green, and anti-blue. The rule for forming color-neutral particles is analogous to mixing colors. Mix red, green, and blue equally. You get colorless. This is how baryons, like the proton and neutron, work. 1 red quark, 1 green quark, 1 blue quark. Alternatively, you can combine a color with its anticolor, a red quark and an anti-red antiquark. This gives a colorless combination. This is how mesons work. Pions, kaons, and the other meson particles consist of a quark and an antiquark with cancelling color charges. But notice that color charge is fundamentally a three-dimensional thing. Electric charge lives on a line. Negative on one end, zero in the middle, positive on the other. Color charge lives in a more complex space. The SU3 group has an 8-dimensional adjoint representation, 8 independent gluons, each carrying combinations of color and anticolor. The color charge of a state can be described by its position in a multidimensional charge space. It's much richer than electric charge, and this richness directly causes the different behavior of the strong force. More generators means more gauge bosons. More gauge bosons means more interactions. The self-interactions of gluons, which have no analog in electromagnetism, arise because the color charge space is so much more complex than the electric charge space. The mathematical richness of SU3 compared to U1 is what makes nuclear physics so much more complicated than atomic physics. Electrons bound by the electromagnetic force in simple Coulomb potentials form the orderly structure of the periodic table. Quarks bound by the color force in a non-abelian gauge theory form an extraordinarily complex landscape. Hundreds of different hadrons. Strong interactions that can only be calculated perturbatively at high energies. Confinement that makes direct calculation almost impossible at low energies. Computational physicists have developed a technique called lattice quantum chromodynamics that puts spacetime on a discrete grid and computes strong force processes numerically. Even with the most powerful computers ever built, lattice QCD calculations of the proton mass require months of CPU time on thousands of processors. The proton's mass comes mostly from the energy of the gluon fields and the kinetic energy of quarks, not from the quark masses themselves. The mass of the 3 quarks inside a proton accounts for only about 1% of the proton's mass. The other 99% is the energy of the strong force fields binding them together. E equals mc squared works in reverse here. Energy converts to mass. The binding energy of the strong force gives the proton most of its mass. Charge, through the mechanism of the strong force, creates most of the mass of ordinary matter. There is a phenomenon called charge conjugation symmetry that deserves careful attention. Charge conjugation is the operation of replacing every particle with its antiparticle. Every positive charge becomes negative. Every negative charge becomes positive. Every quark becomes an antiquark. In a world with perfect charge conjugation symmetry, a universe made of matter and a universe made of antimatter would be indistinguishable. The laws of physics would be the same. For a long time, physicists assumed this was true. Then, in 1956, Tsung-Dao Lee and Chen-Ning Yang proposed that the weak force might violate this symmetry. They suggested experiments to test it. Qian-Xiong Wu performed the crucial experiment. She studied the radioactive decay of cobalt-60, a nucleus that can be oriented in a magnetic field. She measured the direction of electrons emitted in beta decay relative to the nuclear spin. If charge conjugation symmetry held, electrons would be emitted equally in both directions. They weren't. More electrons were emitted in the direction opposite to the nuclear spin. The weak force had a preference. It treated left-handed particles differently from right-handed particles. Li and Yang won the Nobel Prize in Physics in 1957 for this prediction. Wu is sometimes noted for not sharing the prize, despite conducting the critical experiment. The violation of charge conjugation symmetry by the weak force has a profound implication. The weak force treats matter and antimatter differently, not dramatically differently, but differently. This slight asymmetry is part of what Sakharov identified as necessary for the universe to end up matter-dominated. Without charge conjugation violation, every process involving matter would have an exact mirror in antimatter. Matter and antimatter would be produced in equal amounts. They would all annihilate. The universe would contain only photons and neutrinos. No atoms. No stars. No galaxies. No us. The fact that you exist is a consequence of the weak force caring about the sign of charge, treating electrons and positrons slightly differently. In the most fundamental sense, charge is not just about how strong a force is, it's about the symmetry structure of the universe. And when that symmetry is broken, even slightly, the consequences can be the existence of everything we see. So we return to where we began. A battery, a wire, a light that turns on, electrons moving through metal. The simple, everyday magic of electric charge doing what it does. You know now that this is not simple at all. Each electron moving through that wire is an excitation of a quantum field that pervades the entire universe. Its charge is not a property that was assigned to it. It is a consequence of how the electron field couples to the electromagnetic gauge field, a coupling that had to exist because of the demand for local gauge invariance. A coupling whose strength, the fine structure constant, is still not fully explained, whose conservation is a theorem, whose two signs are required by the CPT theorem of relativistic quantum mechanics. The electromagnetic field that propagates the disturbance from electron to electron is not separate from the charge. It is the thing that had to exist the moment you demanded the charge be locally conserved. The photons emitted by the glowing filament of the bulb are excitations of that same field. They carry no charge because the U1 gauge symmetry is abelian, because photons would destroy the mathematical consistency of the theory if they carried charge. The light you see is gauge invariance in action. The universe is holding itself together mathematically, and light is what we see when it does that. Charge is not the beginning of the story. It is the consequence of a symmetry that goes deeper, a symmetry that says, the physics must not depend on an arbitrary local choice, must not depend on where you set the zero of your quantum phase. And from that single requirement, electromagnetism follows, all of it. The force between charges, the wave nature of light, the conservation of charge, the two signs, the photon being massless, the coupling constant running with energy, all of it traceable back to one principle, local gauge invariance. And local gauge invariance itself might be traceable to something deeper still, to properties of space-time, to the structure of quantum gravity, to dimensions we haven't yet seen. The question keeps pulling us deeper, and the fact that it does, that every answer reveals a more profound question waiting beneath it, is the most honest summary of where physics stands. The story of charge is not over. It is the edge where our understanding ends and the unknown begins. Good night.